Hello, we're still in the dBi model. Okay. Now, the thing about dBi model, what we managed to obtain the following density of states, right? When I mean density of states is we started with 3n particles. Instead of particles, we're talking about phonons. Phonons are waves that live inside our solid, right? Now, this density of state is basically going over each omega that are possible to exist, or they do exist in our system. And for each omega, we say, well, how many phonons there are inside this solid? Okay, this is the meaning of d of omega, and the quantity that we got for this d of omega was the volume divided by 2 pi squared multiplied by omega squared divided by c to the second power, and we have a 3 over here, right? So this is the d omega. Now, the next thing that we did, we said that the integral of omega of 0 up to some omega dBi of d omega, right? So the assumption of dBi is I know that there are phonons. I can treat each phonon separately. All the phonons are non-interacting. I just don't know how many phonons there are per each omega. And this is what d omega tells us. Right? So the assumption of dBi, this is omega, this is d of omega. Okay? And dBi tells us that it is a parabolic function of omega up to some specific omega dBi. Okay? This is his assumption. Now, since, remember, what is d omega? This density of states. D omega is basically saying how many phonons per omega there are. So if we are going over all possible omegas that there are in the system, the total number of phonons has to be equal to 3n. Yes? C to the second or to the third? Third? Okay. Third. Third. Now, so we perform this integral, and we obtain that omega dBi was 6 c to the third, what else? Pi squared, and divided by v 1. Okay. This is our omega dBi, and basically this is it, right? So afterwards we say we need to find the free energy of Helmholtz free energy, and then we can take several derivatives with respect to this energy, and we are done. Right? So this is approximately where we have finished last lecture. Now, remember how we obtained this guy. So we know that all these different phonons, they are non-interacting. This basically says that for each omega, there is a very specific partition function. Right? Zi was equals to 1 over 1 minus e to the power minus beta omega h, omega I h bar. Now they are completely non-interacting, so I know that the energy, the average energy, the average energy is what? We have this formula, so U, let's call it Ui, particle, the average energy per particle is simply, we developed this formula once again last time, minus d log of Zi divided by d beta. This is the energy per particle, the average energy per particle, and U, the total energy, is going to be a sum, right? A sum over all I over Ui. So we can compute a single of per each particle. The average energy is going to be dependent on omega I. Then we sum up over all the different omega i's that have in the system. So basically, it is an integral between 0 and omega dBi of u of omega, right? D omega d omega. Okay. This is what we need to perform. Now, but the quantity that we have on our mind, that actually the focus of our interest is not u, is what? No, CV. Okay, CV, which is du to dt. Okay, du to dt. Now, look, all the energy is a sum of the energies per particles, okay, or per phonon in our system, in our case. So instead of saying, well, we have a CV, we can define CV of omega I, right? CV of omega I, which is what? It equals d ui to dt. Okay. So when we want to compute the total CV is going to be what? du of omega to dt, an integral from 0 to omega d by d of omega d omega. So what I'm trying to tell you is, yes, there are many phonons. Yes, all the phonons involve a lot of particles, so the particles are indeed interacting. But our representation in terms of phonons is that all the phonons are not interacting between themselves. The only thing is, the problem to know is how many phonons I have per specific omega. But we know this, we solve this problem. Okay. Afterwards, I can treat each phonon separately. I can compute the partition function per phonon. I can compute the average energy per phonon. I can compute the specific heat per phonon. Okay. And then if I want to compute the total specific heat, I just need to perform this integral. Okay. So the only question is how this du to dt looks like, and then I can plot it inside this integral, and that's it, I'm done.
Stas, זה לא אותו CV, כאילו, השאר השמאלי זה CV.
This is the total CV of the whole system. This is the how CV of the whole system looks like. It's always the derivative of the average energy with respect to the temperature. Okay? But if they're all non-interacting, you see the total energy is what? Is the sum of the energies per particle. So I'm saying that the total CV is a sum of small CVs. Okay, so let me write it down. I'm saying the following thing.
So CV is an
CV,
extensive quantity?
sorry?
CV is an extensive quantity.
If it's, yes. So CV is du to dt. Now I'm writing down that d to dt, u is what? Sum over iui, which is sum over I dui to dt. And what is this? I can call it like a sum over I CV, let's say omega I, whatever. And those are just the specific heats of the specific heat per phonon. All of this possible since they are not interacting. Okay? This is why it's also doable, and this is why it's simple. The moment that I know that I have a representation in terms of non-interacting particles, I can call them phonons or whatever. Okay? Everything else afterwards is just summation of calculation for a single particle. That's it. This is why I need to know this density of state, because I need to know how many phonons there are per each frequency. Yes?
The term of d omega and then the density, it's fit for all kind of...
Basically, well, not exactly. If you go backwards, you see that we have made some specific assumption. We have made assumption that the wave speed, is basically the same for longitudinal and transversal waves. But we know that there are solids that this assumption does not hold for them. Okay, so what is going to change basically is that this prefactor 1 over c to the third is going to be a little bit, so it's going to be modified for different solids. So here we have 3 divided by c to the third. So for different solids, it can be a little bit different, okay? But only this prefactor over here.
And you can describe the velocity.
I can describe the velocity of the waves inside the solid by using different different velocities in the longitudinal direction and then transversal directions. Okay? So, but basically, this is a prefactor that's units of 1 over velocity to the third. It's going to be always the same units, but the exact value can change from solid to solid.
למה רשמת פה את 3 חלקי C בשלישי?
It was there beforehand.
אוקיי. למה רשמנו פה את הדבר הזה במסגרת עם הספציפיקטים?
I cannot repeat this. Okay? This is a formalism, how I develop everything in terms of single particles. Great. So what is left is just to compute this C over omega I. Okay, so we need to calculate. See, this is ui. We need to calculate d to dt of ui, right? Which is, let's call it d to d beta of ui multiplied by d beta to dt. Okay. So I'm going to call it d beta to dt is what? Is minus 1 over k Boltzmann t squared, right? dui to d beta. Now dui to d beta, ui is simply minus d log of zi to d beta. So this is minus 1 over k Boltzmann t squared d to d beta of minus log of 1 over 1 minus e to the power minus beta h bar omega.
Then you put the second derivative.
Second derivative? Why it's second derivative?
Because you're doing d beta.
Okay, great. So this is this, and this is that. Absolutely right. Okay? Okay, so minus and minus, and another minus over here, so we can have minus 1 over k Boltzmann t squared, d squared to d beta squared of a log of 1 minus e to the power minus beta h bar omega I. Right? So let's take the first derivative. The first derivative is 1 over k Boltzmann t squared, d to the d beta of 1 over 1 minus e to the power minus beta h bar omega I, and the inner derivative of 1 minus e to the minus beta h bar omega I is minus 1 e to the power minus beta h bar omega I multiplied by minus h bar omega I. Okay. Let's write it down again. So we have minus, minus, and minus, so we still have equals to minus. Here we have 1 over k Boltzmann t squared d to d beta, and what is left outside is h bar omega, so we can write it over here, h bar omega I. Okay. Here we have 1 over e to the power beta h bar omega I minus 1. It equals to, so we leaving all this prefactor again, h bar omega I by k Boltzmann t squared. This is 1 over e to the power beta h bar omega I minus 1 squared. Here we have minus 1. We have e to the power beta h bar omega I, and we have an additional h bar omega I. Okay, so in total, what we call CV omega I equals to minus and minus, they disappear, so this is great. And we have h bar squared omega I squared divided by k Boltzmann t squared multiplied by e to the power beta h bar omega I divided by e to the power beta h bar omega I minus 1 squared. Now this is only for a single frequency. Now we have to sum up for all the frequencies, right? Instead of summation, like over here. Right? So CV, the total, is the summation over all possible frequencies. Yes.
במעבר מהלוח הזה, כאילו לצד הזה, לאן נעלם האקספוננט במונה?
Where?
Both sides by
I just put it to the denominator. Okay? And then it sweeps its signs from minus to plus, and this guy gets cancelled, so that I have e to the power beta h bar omega I and minus 1. Okay, so CV in total equals to integral from 0 to omega d by what we have inside here, which is h bar squared omega squared divided by k Boltzmann t squared e to the power beta h bar omega divided by e to the power beta h bar omega minus 1 squared d omega, and I don't remember already what we have to do with d omega. What we have with d omega is v divided by 2 pi squared multiplied by 3 c to the third and 1 over omega squared d omega. Okay. So this is the integral that we must solve. We must solve in order to be extremely satisfied or not satisfied with the approach that Debye used. Now, can we solve this integral? Exactly. What do you think?
Yes.
No.
It's too complicated.
It's a very complicated integral, and there I don't think that there is a very simple representation of this integral. Now, so usually in physics, when you're dealing with a complicated problem, there are very few examples when you can exactly solve the integral. In some cases, you just call this integral a special function, beta, or Bessel, or gamma, or there's many different special functions which are simply some specific integrals, and those integrals were important enough that somebody gave them a name, but this is a less important one. Okay. But usually what we can do, we can solve integrals when we have specific limits. So when one of the arguments that lives inside this is either very big or it's either very small. Okay. So this is what we are going to do. We're going to find a solution in two limits. And those are the usual limits in physics and in statistical physics over here, is that we're going to look on t goes to infinity, and the second limit is t goes to 0. Now, remember that this omega dBi over here, is something, right? So omega dBi, let's write it down over here so we won't get confused. This omega dBi is 6 c to the third. What we have over here yet is v pi squared n pi squared n v, and all of this to 1/3. Okay, so I'm going to use large t and small t in order to solve this integral because I'm capable of solving it. Now, look on this integral. So omega is the variable that I'm integrating over. So all of those are good. We can take a lot of stuff out, like h bar squared, k Boltzmann, t squared, 3v. All of those are getting outside. Okay. So we write this down, the CV equals to, let's take everything out, like h bar squared, omega is kept inside, k Boltzmann, t squared. What else do we have? 3v, right, 3, 2, v over here. We have pi squared, and c to the third. Okay. So what we are left with inside, this is an integral from 0 to omega d pi. And here we have omega to which power? To the fourth. E to the beta h bar omega divided by e to the beta h bar omega minus 1 squared d omega. Okay, this is not such a nice integral. Why? Because, well, I want to get rid of this beta h bar omega that stands inside. I want to get rid of it from the integral, maybe get it outside of the integral itself, or introduce it into the limits. Right? So I basically say beta h bar omega equals to x. You want t?
No, it's good.
X is good. Okay. X. Doesn't matter. Okay? Now, so what is d omega? So d omega is 1 over beta h bar dx. Okay? And omega is equals to x divided by beta h bar. Okay. So we are going to introduce all of this inside the integral. Some of the parts are going to get out, and this limit is not going to be affected. 0 will stay 0. Omega d pi will be something else. Okay, so what we are left with is equals to all of this prefactor, right? So we have it 3h bar squared v divided by 2k Boltzmann t squared pi squared c to the third. Okay, now we have from this guy d omega, we have 1 over beta h bar. And from this guy, we have 1 over beta h bar to the third. So in total, we have 5. And here we have an integral from 0 till omega d pi. What is omega d pi is multiplied with? Yeah. So I don't like this big expression. So when omega equals to omega d pi, x equals to? Okay. Are you sure? So what do I put over here? Omega d pi multiply divided by beta h bar? Lechalek? Okay. Divided by beta h bar. This is the claim. No?
Multiply.
Yes or no? So what is the maximal x? Multiply. So maximal x is x grown from 0 when omega is 0, x is 0. When omega equals omega d pi, x equals to beta h bar omega d pi. Beta h bar omega d pi. And what we have inside? We have inside x to the fourth, e to the x.
Minus x, no?
Why minus x?
No,
No, it's good, it's good. E to the x minus 1 squared dx. Now this is good. Why it's good? So I have all these prefactors, right? All of those guys. First of all, if we are treating with limits of t goes to infinity and t goes to 0, I want to write everything here not in terms of beta, but in terms of t. So let's write, first of all, everything in terms of t and see why the thing that we're left with is actually extremely good for those two limits. Okay, so first of all, what we have this is h bar squared, h bar to the fifth. So we have 3v 2k Boltzmann pi squared c to the third. This is still the same, right? Now, here we have h bar to the second, h bar to the fifth. So we are left with 1 h bar to the third. Here we have, I'm sorry, k Boltzmann is also, we will translate it somewhere else. So now, here we have 1 over k Boltzmann to the fifth. So it's k Boltzmann t to the fifth, right? So we're getting t to the third, okay, divided by k Boltzmann to which power?
4.
To the 4. K Boltzmann to the 4. And all of this multiplied, integral from 0 to omega d pi divided by k Boltzmann t.
H bar for sure.
H bar. Okay, this is good. So this is unitless. Energy divided by energy. Okay, so we're fine. X to the 4th, e to the x minus 1 squared dx. The prefactor is not interesting. The prefactor is absolutely not interesting. What is interesting is t to the third and whatever stands over here. Okay? Why it's interesting? So in the limit, when t goes to infinity, h bar omega d pi divided by k Boltzmann t goes to 0. Okay? Very nice. Why it's nice? When the limits of the integral is from 0 till something extremely small. Right? I'm looking on very large temperatures, so the upper limit is very small. I know that all the x's are small. X is approximately 0 everywhere.
So the answer is 0?
No, the answer is not 0. The answer cannot be 0. What I mean is that I can expand or use Taylor series in order to expand e to the x and e to the x over here. And I'm only interested in the first term. What is the upper limit? The upper limit, so this is 0, and the upper limit is extremely, extremely small. All the x's are between the lower limit to the upper limit. So if it's a very short interval around 0, so all the x's have to be small. Okay?
רגע, x לפני אינטגרציה זה כפל, נכון?
Oh, so this is multiplication. In order not to disrupt you, multiply. Okay, so this stays the same. E to the x, it's approximately 1 plus x, right? Okay. Now, so I'm looking only on this integral, and I'm looking on an integral from h bar omega by k Boltzmann t in the limit of t goes to infinity. And inside, I have the following. So I have x to the 4th. This is good. E to the x, I'm keeping only what? Only 1. Okay, let's write it with the plus x, but you will see in a second that it doesn't matter.
It's higher order?
It's a higher order. We won't need this higher order. Now, here, I'm plotting 1 plus x minus 1 to the second power. So this equals to integral from 0 by h bar divided by k Boltzmann t, x squared, 1 plus x, divided by x, this is x fourth, x to the second, dx. Now I'm looking only to the first, on the first order of this integral because t is extremely, extremely large. So this is extremely, extremely small, and I only care about the first order. Now the first order, I don't need this x. Okay? It's the next order approximation. Okay? So I simply say, well, this is approximately h bar omega d pi, omega d pi here, omega d pi, yes, omega d pi by k Boltzmann t. And here we have x to what power? X squared, right? dx. okay, which is equals to 1/3 h bar omega d pi divided by k Boltzmann t to the third power. Okay, so this is the first limit. Right, this is only the first limit. We go here and we put everything back inside. We will still keep this omega d pi in place. This might look difficult, but this is actually the easy part of whatever we've been doing for the last 2 lectures, right? The problem was the physical problem where d pi started. The problem was to identify that Einstein was wrong. The problem was to identify that we should talk in terms of phonons and not of particles. The problem was to calculate the density of states and the continuous spectrum. Those were conceptual problems. They might be a little bit less technically difficult than what we are doing right now, but they were new ideas, not technical ideas. Whatever we are doing over here with those integrals, this is simple, right? Really simple, because it's not about physics. It's about solving an integral that might sound difficult to you or look difficult to you, but the difficult, really difficult part was the change of mind that people had to perform. Instead of looking on particles, I'm looking on waves. And how I treat with those waves, and that the waves are not interacting, etc., etc. Those are the difficult parts. This might be cumbersome, this might be a little bit hard to follow, but this is technical. Yes?
אני לא כל כך הצלחתי להבין למה התעלמנו, כאילו, למה אם אנחנו מסתכלים בגבול של t שואף לאינסוף, אז ה-t בשלישית שמחוץ לאינטגרל לא משהו.
Okay, so the question is why I only care about this part and not about this part. But I'm not assuming anything about this part. This can be as big as I want. I don't really care. This is already an exact expression. The only thing that I really don't know is how this expression looks like. Okay? So this is enlarged limit or enlarged t limit or in the small t limit. It's still going to be some constant multiplied by the t to the third. It doesn't matter. The only thing that's going to change is how this term looks like. All of this integral. Okay? So this is the heart of the approximation. Okay, so what we're left with is let's put everything back inside. So this stays the same, and this is something new. So we have CV equals to 3v 2 pi squared c to the third 1 over h bar to the third k Boltzmann to the fourth, t to the third, right? Multiplied by 1 over 3, h bar omega d pi, divided by k Boltzmann, t to the third power. And omega d pi is this nice thing over here. Very nice. Now, first of all, what do we see? Look, t to the third and t to the third. We're getting that in the large temperature limit, the specific heat is independent, totally independent of what? Of the temperature. This is we see immediately. Now this is good because this is also what we observe in an experiment. Okay, so let's find out what is the exact expression. So we have 3v 2 pi squared 1 over c to the third 1 over h bar to the third k Boltzmann 4 t to the 3 1 over 3 h bar to the third k Boltzmann to the third t to the third multiplied by what we have here to the third power. Multiplied by this guy. Let's write it down. 6 c to the third pi squared and divided by v. Erase it. Okay, let's start and kill all the terms. V and v. 3 and 3. C to the third, c to the third.
T.
Pi to the squared, pi to the squared. H to the third, h to the third. T to the 3 to the 3. K Boltzmann to the 3. This is 1 and 2, and here we are left with 3. And in total, we obtain a very nice result, which is 3 K Boltzmann multiplied by N. So 3N multiplied by K Boltzmann. And miraculously, this is also what you get in an experiment. Okay, so the method works, and this is also what Einstein has predicted. Okay. This is nice. Getting all of this done, and eventually everything is somehow discussed.
You didn't refer to t goes to 0.
Oh, right. That was the problem, of course. So, but at least device deals as good as Einstein in the limit of large temperatures. Okay? Of course. Now the second limit. So we're going over here. So we will discuss later, not today, I won't have time today, but why from first principles, I should expect for any system at high enough temperatures such a result. So this is not the Einstein model or the Debye model. This is an outcome of something that we called equipartition theorem. Equipartition theorem. We'll learn about it on Sunday. But any model that dealing with real life physical system should give this result. And we will see why. At the limit when the temperatures are high enough. Okay, so what is going on in the limit when t goes to 0? T goes to 0.
שם AR בין A ל-T?
Equipartitio. Okay, so h bar divided by h bar omega Debye. Omega Debye is independent of temperature, so the only temperature that we have over here is in the denominator. So all of this goes to infinity, okay? And I can no longer assume that x equals to 0 or approximately 0. So whatever I have over here is simply wrong in this limit. But this is actually the easier limit than the limit of high temperatures. Why? Because so h bar omega Debye divided by k Boltzmann t goes to infinity. We are interested in the behavior. I said before, this stays the same always, right? So this is a known fact that the prefactor is a constant multiplied by t to the third. The only thing that I do not know how to behave is this integral over here. Okay. Now I know that the upper limit goes to infinity. So so the only thing that I'm going to do is to write this down as an integral from 0 to infinity of x to the fourth e to the x divided by e to the x minus 1 squared dx. And the solution of this integral is it's independent of x, it's independent of t, it's independent of v, it's independent of anything that stands inside this. It's a number. So what number? Well, use a Wolfram integrator and see whatever it equals to. Okay? But it's a number. Something, something, something. We don't care. Okay? Now, the moment we have this number, we're practically done because we're going back to this expression, and the only thing that is left is to multiply this by a specific number. Okay, so CV, t goes to 0, CV goes to 3v divided by 2 pi squared, c to the third, multiplied by 1 over h bar to the third, k Boltzmann to the fourth, t to the third, and we have an a over here. This is a prefactor, which is something. It depends on the volume of the system. It depends on the wave velocity inside the system. And you remember, it's not always 3 divided by c to the third. It can be something a little bit different because we have transversal waves and that's way and the longitudinal waves. But all of this is a constant. The main factor is that it's proportional to the t to the third power. And remember, this is exactly the limit. This is why you asked me. This is the limit where Einstein failed. Einstein failed in the limit of low temperatures, because in the Einstein model, it was going, CV was proportional to E h bar divided by K Boltzmann T. And when T goes to 0, or with a sign of minus. So all of this, we're going to 0, the specific heat was going to 0 exponentially fast. This was the problem. The problem of the Einstein model, that the specific heat was decaying to 0 extremely fast. And when we were looking on this in the log scale, taking a logarithm of CV versus a logarithm of temperature, they were uncomparable. But the experiment, what exactly the experiment shows? The experiment shows that the specific heat of a solid, it's a constant, and now we have a specific description of what this constant might be, multiplied by T to the third. Okay? So, in this sense, the Debye model was a huge success. Huge success, right? Because it was capable of triumphing in the place where Einstein failed. And what is the main difference? So the difference is not that Debye was capable of computing some strange and hard integrals that Einstein haven't thought about them. No, the success was in the proper physical description, proper physical modeling of whatever is going on inside. Okay? He haven't assumed that all the particles are independent from each other. He assumed they are dependent. But there is a way, okay, in terms of waves, to describe everything as if they are still independent particles. So this is a new way of thinking, okay, in thermodynamic waves, in the language of thermodynamics. I do not think more about particles. I invent new particles. Okay? I absorb some particles together and say this is a new particle, that is a new particle. And now I can find a way where all those new particles are independent, and this still works. And this still works fantastically, because this is a failure and this is a great success. Okay, we will stop over here, and next week we'll learn more about the equipartition theorem and why at large temperatures it is always the number of degrees of freedom that we have in our system multiplied by K Boltzmann. It is always the case in any physical system, in any thermal system. This has to be the case. This is one. And also we will see how all of this description of waves inside solids and etc. is actually the same way of describing a problem that you have heard about, the black body radiation. Okay. See you next week.